So what if the patient's decision does depend on the message? So let's assume that the probability that the state of the world that is revealed to the doctor is 0. Okay? However, the message that he sends to the patient is 1. And this is done with any probability because all probabilities are consistent. Priors and posteriors are the same, so this could be 1, half, fourth, doesn't matter. Whatever p, with any probability. In this case, we're going to assume that there is a decision rule, a particular action that is taken when the patient receives the signal 1. This is y prime. So in a particular action, when the patient receives signal 1, he will choose 0. What this means is that we're assuming that the patient is implementing a new rule. Okay, so where the patient chooses y equal to 0 when he receives the message 1. Otherwise, he implements the y equals half. Here, we will show that this is not part of a pooling equilibrium. Why? Because we have to think about sequential rationality. And sequential rationality, in order for it to hold, the doctor has to compare his payoff from sending another signal. He is going to be, therefore, checking for a profitable deviation. Is it always then profitable simply to send the signal m equals 0, or is it profitable for him to in fact send a signal 1? Would it be a profitable deviation? When all doctors send m equals 0 and say one doctor sends m equals 1, is it profitable? Like in the simpler version, this information set is never reached. Remember my drawings? We're dealing with a pooling equilibria where we have m equals 0. And we're supposing that one of the doctors is considering whether he should deviate from sending the same message or not. Of course, in this case, we only have 2 types of doctors, right? And 2 types of messages, where what we're considering is, in fact, a multiplicity. He could be any message. It doesn't need to be m equals 1. It could be m equals half, m equals 1/4, m equals whatever, okay? However, because we're checking for a pooling equilibrium, this information set is never reached in a pooling equilibrium. Unlike the previous case, there are many types which receive many different messages, and we want to check if there is a type that can profitably deviate. So let's explore one possible deviation. Assume the doctor is a type X plus B. The doctor has many options, of which 2 are she can send message 0 and patient chooses half, and payoff to the doctor is therefore m equals 0, y 0, right? Payoff is half, and then the payoff to the doctor would then be x plus b minus half minus b squared, which is equal to 0. Why? Because this is half. or she can deviate. And she can choose to send message 1. And the patient will then implement his new rule, right, when he receives message 1 and choose 0, for in which case the utility for the doctor will then be x plus b minus 0 minus b squared equals 0, because x equals 0. So in this case, the patient believes that the doctor is type 0. So the doctor is deceiving the patient. Okay? This is what's happening. The implementation of this rule by the patient is assuming that the patient is being deceived in some way. Therefore, the doctor is indifferent from sending m equals 0 or m equals 1, and can be a profitable deviation because he is indifferent. Now assume that the doctor is type B. Again, if m equals 0, so if the message of the doctor is equal to 0, the implementation rule will be that the patient will choose half, which is equal to, let's cancel out, -4th. Okay. Or if she deviates to m equals 1, the implementation rule of the patient says that now he chooses 0 when he observes 1. And the utility of the doctor will therefore be b minus 0 minus b squared, which is equal to 0. Therefore, the doctor has a definite profitable deviation. He will always prefer to send the message M1 because he receives a higher payoff. In essence, what this game is all about is that in the event, therefore, where everything is known and the patient chooses Y, his utility is 0. Otherwise, his utility is going to be negative. The doctor's loss function is the same, other than it wants to move B units to the left of the patient's choice. The larger the B, or the bias, which is commonly known, the larger the conflict of interest. The only unknown is the state of the world, and the patient wants to extract information from the message. Now, the only way we can do this is by investigating how we can identify partially separating equilibria. And one way that was discovered to do this in this formulation of the game was by setting boundaries where different types send different messages. So remember, partially separating equilibria, where different types send different messages. In statistical terms, the types are statistically dependent on the messages. And this was a formulation that was designed by Sobel and Crawford. Imagine our unit interval. Okay. And we're going to just set a threshold x star. And we're going to say that there is a message 1, which is low, and a message 2, which is high. So we're going to allow the doctor to send only 2 messages, as we've shown here, M1 and M2. So M1 is going to be sent if the state of the world is between 0 and X star. Thus, the doctor sends message low. With respect to M2, we can easily assume what's going to happen now. If the state of the world is between X star and 1, the doctor sends message high. So when the patient receives the message, he knows about the threshold and infers whether he is above or below X star. Therefore, what is going to be the patient's best reply? Right? So sequential rationality is going to be to maximize the expectation of his utility function given the information he's received. Note that expectation is a linear operator, some sort of a sum of values multiplied by probabilities, and therefore it is linear in whatever is inside the expectation. Okay, I'm just going over this with you again. I'm going to write this down. Nota bene. This allows us to take the first order condition of what's inside the expectation. Okay? So if we take the first order condition of the expectation, minus x minus y squared given I, right, equal to 0, we find, as we did before, that it's 2x minus y given I equal to 0. Since the expectation is a linear operator, this means that the expectation of a sum is the sum of an expectation. And remember also that y is a choice variable. There is no randomness in y, and therefore the expectation of y is simply equal to y. So all we have to do is find y star in order to find the best reply for the patient. The objective function of the patient is variance. In statistics, it is the second moment of the distribution of x. In fact, the best linear predictors are expectations. When you want to predict a random variable such that your prediction minimizes the dispersion, the best predictor is the expectation.